throughout our daily life. So what we are going to cover today is just 3 topics. Okay, and this is considered the last topic for this semester and for this course. Okay, so basically we need to understand graph representation and 2 basic techniques to explore. Okay, in comparison to binary tree, we have 3 traversals in order, pre-order, and post-order traversal. But in graph, we don't have in order, pre-order, post-order anymore. What we have is 2 new techniques called breadth first search and depth first search. So these are the only 2 traversal techniques we use in exploring, in processing graph. And what you need to do is to read a little bit more to this topic, difference between breadth first search and depth first search. Okay, so that's the thing that we are going to cover. So I'll start very briefly on the graph and its representation. Okay, graph. And we can formally, the keyword formally means in mathematics. Okay, whenever we say formally, that means in mathematics. We can define a graph as a set. Okay, any graph data structure can be defined as a set of 2 subsets. Okay, it's a set of vertices and a set of edges. So basically, we have 2 sets, set V and E. V is a set of vertices, E is a set of edges. In combination between these 2 sets, we have graph. So we generally write or denote graph by G in parentheses VE, GVE. This is how we actually use the notation for the graph data structure. Okay, so we actually have many types of graph, but what we were to cover today, the few of them. Starting with the first and very simple one, is called unweighted graph. Unweighted graph, which means we have simply nodes of vertex and edge. Okay, so basically we have simply like this. That's this graph. Okay, if you look at the way we draw the picture of graph, it's very similar to the tree, except that we do not organize nodes or vertices into levels. No level anymore. What we consider is the connection of edges between 2 nodes or 2 vertices. And this one graph consists of 3 vertices, 0, 1, 2, and 3 edges, 0, 1, 1, 2, and 0, 2. Okay? So when you write the notation of the graph, you can write it in mathematical sets. Okay, so I would like to take everyone to our classroom. Okay. Go to classroom and you have the slice graph is here. Okay, is on September 15. September 15, okay? The material graph is there. Okay, so we have two slides here, graph 1 and graph 2. That's all about the three topics that we are going to cover today. Okay, so if you look at, I just want to show you that when we talk about graph, with this representation in mathematics, we can actually write it like this. This is the definition of a graph again. Consists of V and E. V is a set of vertices. E is a set of edges. Okay, and as a set of edges, one edge, okay, can be represented in this format. This ordered pair, VW, or XY, whatever. V is a name of a node in set V. W is also a node in set V. Okay, so that's how we can actually write a combination of V and E in a graph G. This is one example. Okay, what I want everyone to look at is on this right hand side. On the right hand side here. Okay, you can see that V is a set of vertices. Now we have vertex A, B, C, D, E. So that's the list of 5 vertices for 5 nodes. A set. And E. Now, in this slide, you can see that each edge on this picture has a label which represents the name of the edge. This is one difference from tree. In tree, you don't have a name for edges, but in graph, you can actually name edges. Here we have E1, E2, E3, E4, E5, E6, which is the name of these 6 edges. Okay? And that's how you can represent edge by name, or you can write it like this. Look at this. Edge in parentheses A, B. A, B. That means it's an edge between node A and node B. That's it. Is that clear? That's how we write an edge. In this one, we have spatial edge. We have spatial edges. One, if you have 2 edges connecting between the same 2 nodes, like this E4 and E5. Look at E4 and E5. We call it parallel edge. Okay? E4 and E5 are considered parallel, so we call it parallel edge. And if spatial edge E6 connect between C and C, same nodes. Okay? If an edge is connected between same nodes, we call it loop, self-loop. That's it. Okay? So that's an example of the graph. And here, what I want everyone to know is we have different terms with the graph, starting with between these two, the simple graph and complete graph. Okay, simple graph and complete graph. What is the difference between simple and complete? We have walks, trails, paths, cycles, circuits. These are keywords we need to learn today. Afterwards, we will move on to weighted graph, direct graph, and undirected graph. So that's all about the graph that have different types of graph that we are going to cover within this topic. And we have the concept degree as well. Okay, so starting with the first one, let me show you the definition of the graph and its representation. It's over here. So the link is Introduction to Graph Data Structure. Okay, it's on this page, starting from graph here. You can click on this link graph and this representation, and on this representation, the link is here, graph. Okay, let's go to this one, Introduction to Graph Data Structure. In this page, all properties will be written there. So basically, starting from the content of the graph, which is the edges which is covered. Okay, now we are having different types of graphs. Okay, starting with the first one is called null graph. What is null graph? Null graph is when we have no edges at all. Okay? Null, which means nothing, doesn't mean no nodes, but we have nodes without edges. Okay? For example, this is considered null graph. And a graph is trivial when it has only single vertex, like this one. A single node, single vertex is called trivial. Okay, so that's considered the smallest graph possible. Okay, in next semester, there are some algorithms that we need to create trivial graph first, and then the graph will be created bigger and bigger starting from the minimum one. Okay, from the smallest trivial graph. So that's the keyword you need to know. And undirected graph is here, and directed graph. Basically, just look at edges. When the edge within the graph has no direction, it's not arrow. It's just a line. We call undirected graph. But whenever you write an edge with an arrow, whenever edges is written with arrows, then it is called directed graph. And this actually means a lot. This actually means a lot. Because today you are going to learn walk, trail, circuit. That is, starting from one point, one node, from 5, for example. In this graph, undirected graph, you can see that from 5 you can go to 3. And from 3 you can go back to 5. But on this graph, when you have this edge written as arrow, it means from 5 we can go to 3. But from 3 we cannot go back to 5. Okay? So the direction gives you the meaning of traversal between one node to another node. Okay? From this undirected, it can actually mean 2 directions, back and forth. Okay? But this is one direction, one way. Okay? One way, two way, back and forth. Okay, now we have two keywords, connected and disconnected. Okay, a graph is considered connected when you have to read this carefully. It's connected graph when at any node, not just one node, okay? From any node, you can go to every other nodes. For example, you have 5 nodes. If you select node 1, you must be able to go to 2, 3, 4, 5. Or if you select node 5, you must be able to go to 1, 2, 3, 4. Okay? At any node, you must be able to go to other nodes, every other nodes. And that is considered connected graph. You can see that in this graph, we have on the left, from 4, you can go to 5, you can go to 1, and you can go to 3 via 5 or 1. 4, 5, 3, or 3, or 4, 1, 3. Okay? And from any nodes, from 5 you can go to 3 nodes. From 3 you can go to 3 nodes. From 1 you can go to 3 other nodes. That is considered connected. But this one, on this side, you can see that 5 can go to 3, but we have no way to go from 5 to 1 or 4. That means the graph on the right hand side is disconnected graph. Disconnected. Okay? So that's the two different properties of the two different types of graph. Okay, now we have complete and regular. Okay? Complete graph is not complete tree structure. It's different, but we use the keyword complete. Let's have a look. Starting with regular. Okay? The graph in which the degree of every vertex is equal to k is called k regular graph. Once again, the degree, we have two things to note here. The degree. What is the degree? The degree is the number of edges connected to each node. So if you look at this graph on the left-hand side, we can see that each node, starting from node 3, we have 1 edge, 2 edge connected to node 3. Node 5, how many edges connected to node 5? 1 and 2. 4, 2 edges. 1, 2 edges, okay? So basically we have to count the number of edges connected to each node. If the number of edges of every node are equal to our value k, we will call this graph k regular graph. In this one, every node has 2 degree, the degree 2. So we call 2 regular graph. And this one, every node has 3 edges. So it's 3 regular graph. But whenever it's 3 and the number of node is 4, okay? When the number of node is 1 plus k, we call it complete graph, which means each node there is an edge to each other node. Okay? This is, you have to imagine that at each node you have direct edge to other nodes. Okay, that is called complete graph. difference complete graph. I'll show you the picture. Images of complete graph. In a complete graph, we will write a notation like K with subscription of number of nodes. For example, like this. Okay? K2, K3, complete graph. K4, K5, K6, K7. Okay, so that's the complete graph. And if you have a bigger than this, like this is K8. So each node has an edge to 7 other nodes. That's K8, K7, K6. Okay, so that's how we imagine the complete graph. We generally use to write nodes in circle because it's easy to draw the complete graph. Okay, so that's the complete graph compared to regular graph. Okay, regular graph, each node has same degree, but when that same degree is maximum, it's complete. Okay, now we have cycle and cyclic. Cycle and cyclic. What is cycle? When the graph is a cycle, the minimum value degree of each vertex is 2, like this. This is a cycle, which means every node has degree 2 at the minimum. It's not regular, okay? Which means every node must have the degree at minimum 2. You can have 3, 4, 5, that's okay. But it at minimum is 2 for every node. And that's called cycle. But like this one you can have a look at this node 5. Node 5 is the only node which has degree 1. Okay? So this graph is not cycle. But we can always go to every other nodes. That means we don't have cycle, but we have cyclic. Okay? A graph is called cyclic when it contains at least one cycle known as cyclic graph. Okay? And that cycle is here. The cycle. Okay? A cycle graph means the whole graph is cycle. But part of it is cycle is called cyclic. Okay? And this is the one that we use the most. In many computer application, we need graph with no cycle. We call acyclic. No cyclic. And it is directed graph as well. So if you have a directed graph without cycle, you call it directed acyclic graph. And we usually use the acronym DAG, which means directed acyclic graph. That's the common words that we use. Vital type is a little bit too much to skip. Weighted graph is where in the graph, each edge is labeled with weight, number, this number, okay? Okay, so that's all about the basic of the graph. So let me go back to our classroom. Now, there are some terms all about it's actually the thing that we use in algorithm. We need some keyword, walks, trails, paths, cycle, and circuit. 1, 2, 3, 4, 5 terms, which are related, but they are a bit different. So let's have a look at the definition. Okay. Start with a walk. A walk is a sequence of vertices and edges in a graph. If you traverse the graph, you get a walk. That is a very simple concept that we are going to learn today. Every other keyword trails, paths, cycle, and circuits are built on walks. So we need to understand what a walk is. So this is one example of a walk. Okay? If you start from A, and then you walk along edges from A on edge 1 to node B, on edge 6 to node D, on edge 5 to node C, on edge 4 back to node B. This is considered one walk. Or you can also from A to B to D to C to B back to A. That also another walk. So basically, when you're starting from node, follow an edge to another node, and on and on and on, that's considered a walk. And it doesn't matter how many edges it takes. You can actually starting from E to F and stops. That is another walk, the shortest one. Okay, because this one edge is used. And this is one example of the walk. Okay, let's have a look at this one. So if you look at this sequence, A, 1, B, A, 1, B, 6, D, starting from A, stop at 1, we call it circuit. Okay, so that's it. Okay, so basically a walk is a general walk. It's general walk. But whenever you have the starting and the last one, it's called circuit. Let's have a look in more details. Okay, trail is an open walk. No edge is repeated. Here is one restriction. No edge can be used twice. Okay? One edge, an edge can be used once only. That is called a trail. But the vertex can be repeated. Okay? So if you have like this, you can see here, this is a simple one. So when you're starting from one node, following an edge to another node, Okay? No matter the edge is repeated, no matter which note is repeated, we do not care. That is called a walk. Okay? But whenever you can see, whenever you want a trail is a walk with no edge is repeated. So in this one, you have another walk. Look at this. This is a walk from A to E. A walk from A to E. And you have B. Repeated. From A to E, B repeated. But 1, 6, 5, 4, 7. These edges, no one is repeated. So this walk is trail. Okay? When you have a walk, you have to consider if no edges is repeated, it is a trail. Okay? And when it is a trail like this, A, B, E, F, D, B, C, A. Oh, we have B repeated. 1, 2, 7, 8, 6, 4, 3. No edge is repeated. It is a trail, but it is a spatial trail. Okay? This one is trail with open trail. Open means the first and the last note is not the same one. But this is called close. And when we have a close, A, stop A. Start with A, stop with A. If close trail, special name for close trail is circuit. Okay? So that's the difference between these two terms. Go back again, read it once again. A walk is a sequence of vertices and edges. That's it. Simple definition. One restriction, no edge is repeated. No edge is repeated. Is trail. Edge is not repeated. Vertex can be repeated. And it is close. Is circuit. Okay? So circuit and trail is basic. You can say that circuit is a trail with close property. Close means the first and the last is the same. That's close. So we call it circuit. Is it clear? Okay. Now let's go on to this one. From walk, trails, circuits, we have path and cycle. Path and cycle. What's path? Path is a trail in which vertex is not repeated. So basically, no repeated vertex, no repeated edges. That is called path. And whenever the path is close, it is cycle. Whenever the path is close, it is cycle. Okay, so this is the example of, can we actually have an example? Oh, no. Okay, so let's have a look here. Okay, you can see that this trail has B repeated. Okay, so it is trail, not path. If you want to create a path, you must not have repeated vertex in your trail. So I can go from A, B, D, C, and stops here. A, B, D, C, stops here. Okay? So that's, I have a path from A to C. Okay? But if you go further, you have B repeated. You break the property of path and you have a trail. Is it clear? Okay. Again, here, the circuits. Okay? When you have a circuit, you can have repeated vertices. V is repeated. It's okay for circuits. Okay? But whenever you have no repeated vertices, then you have cycle. For example, if I go from A, B, D, C, back to A. Okay? So we have A, B, D, C, A. You can see that we have the first and the last, the same one. So it's close. And in between, no repeated vertices. We have B, C, D. And we have one edge, on one edge. No repeated edge. Okay? When we have no repeated vertex, no repeated edge, this is called cycle. Okay? When it's closed. So basically, you can actually say that we have spatial requirements like this. Let's say in a walk. You have a walk, okay, and you have spatial property, okay. So if you have a walk in this area, let me put on. So this is the area of walk, okay, and if you have spatial one, okay, the property is no edge repeated. Okay? If you have a walk with no edge repeated, then you have what's called trail. Okay? If you have a walk with no edge repeated, you have trail. That is spatial walk with no edge repeated. Okay? And if you have a walk with no edge repeated plus close. The concept is close. Then you have what's called circuit. Circuit is spatial trail with closed property. Okay? So let's say this. Circuit. So if you have a walk with no edge repeated, it's trail. And a trail with closed property, it's called circuit. Okay? And if you have one more, okay? For repeated, it's called half. Okay, you can say that and when it is close as well, it is called cycle. So this is the relationship between the four. Okay. So basically, every walk is a sequence of vertex and edges. If that walk has no edge repeated, it's a trail. And if it has no edge and no vertex repeated, it's a path. The trail, if it's closed, it's called circuit. And a path, when it's closed, it's called cycle. Okay? So this is the spatial property of circuit is closed trail. Cycle is closed path. That's it. So that's the relationship between walk, trail, path, circuit, and cycle. Okay? Okay, another keyword in graph is called subgraph, which means just a subset of graph G. Basically, if you have G, is a combination of set V and E. Subset of V and subset of E is called subgraph G. This is the definition of it. A subgraph G can be written G dot or G prime, okay, whose vertex set and edges is subset of graph G. That's it. Okay, and then we have the degree. Okay, now please have a look at the terms degree once again. You know that we can actually count the number of edges connected to each node. And the number of edges connected to each node is considered degree for that node. Degree for that node. For example, this node D has a degree 2. Because 1, 2. Okay? And this node A has degree 2. 1, 2. Look at B. B has a degree 3. 1, 2, 3. Okay? And node C is very special. Look at the degree. 1 to E to D. 2, 3, and 4, 5. Okay? So basically just count the connected points. Okay? Even the same edge, that is okay. So you have 1, 2, 3, 4, and 5. So the degree of C is 5, and E is a very special one, which is not connected by any edge. So E degree is 0. Okay? And it's very typical that we call a vertex with the number of edges, even or odd. If it's 0, 2, 3, 2, 4, 6 with even number, we call it even vertex. But when the degree is 1, 3, 5, 7, odd number, we call it odd vertex.
Degree.
Odd vertex. Okay? So the degree, the number of degree differentiates between odd and even vertex. We have okay, and the degree in directed graph is a little bit different from degree in undirected graph. Because in undirected graph, we just have the word degree. But in directed graph with arrows, we have out degree and in degree. So basically the direction of edges will give the direction of in or out degree. Okay? Like this one, this arrow in into A is an in degree of A. And this arrow again is out from B. So it's out degree of B. Same edge, in degree of A, but it's considered out degree of B. Okay? So if you look at node A has one incoming edge and two outgoing edges. We consider in degree of A is 1, out degree of A is 2. Okay? Look at this node B. Node B has 1 out, 2 out, 3 out. Out degree is 3. Node B has no incoming edge. So in degree of B is 0. Okay? Which means in undirected graph like this, we have just one probability degree for each node. But the degree in directed graph, you have 2 types, in degree, out degree. Okay? And we actually have relationship of the degree and number of edges and number of vertex in the graph as follows. Let me show you in this. Let me find you the number of properties in the graph. Properties of graph. Basic property of graph, that's very easy. Okay, so basically in a directed graph, the number of in degree, summation of in degree of all vertices must be equal to summation of all vertices out degree. Okay? In degree and out degree for each node. Summation of in degree, summation of out degree must be equal. Okay, so that's one property of the degree. And let me sorry, the list of property is not listed here. So basically, we can actually write the formula like this. Let me write it down for you. Okay, now degree. Degree. Okay. Rule number 1: summation of in degree must be equal to summation of out degree. Okay, this is one rule for directed graph. Okay, let's say called digraph in short. It's called digraph in short. Okay? And rule number two, let's say summation of degree of all nodes equal to 2 times the number of edges is 2e. When e is the number of edges in the graph. Okay? So you can actually check if the graph is balanced or not according to the summation of degree of all vertices of all nodes. This must be 2 times the number of edges. For example, let's go back to this diagram. Let me show you this simple one first. Okay, let's have a look at this graph. This graph A. Okay, you can see that B has a degree of 2. Degree of A is 2. Degree of C is 2. So basically we have 2, 2, 2. Summation of 2 to 2 is 6. 6. And 6, we have how many edges? 3. We have H1, H2, H3. So it's 6 equal to 2 times 3. Okay, so that's the property. And if you look at this graph, you can see that we have A has in vertex 1, out degree 1, so 1, 1. B 1, 1, C 1, 1. Okay, in degree of A is 1, out degree of A is 1, in degree of B is 1, out degree of B is 1, in degree of C is 1, out degree of C is 1. Okay, so add, you can see that summation of in degree is 3. Summation of out degree is 3. And summation of in degree equal to summation of out degree equal to number of edges. Okay, so that's the property of derivative graph. So you can go back here and summation of in degree equal to summation of out degree equal to some number of edges B. Okay, so that's the property of degree for each graph. Okay, so that's probably all the properties you need to know within the graph. And next is, what is next? Okay, we will have this representation of the graph. Okay, so basically, to represent a graph, we have two different types. One is using matrix. We call adjacency matrix, which going to have the number of rows and number of columns according to the number of vertices. In this graph, you have 1, 2, 3, 4 vertices A, B, C, D. So you have 4 rows, 4 columns. If you have 5 vertices, you have 5 rows, 5 columns. You have 10 vertices, 10 rows, 10 columns. Each value represents an edge between 2 vertices, between 2 nodes. Like this one, represent from A to B. This one, from A to B, from A to B. This one, from B to A. And it's 1 because we have an edge from A to B. And you can see that A to A is 0 because we don't have an edge from A back to A, no self-loop. But here, C, we have a self-loop from C to C. That's why we have C as 1. From C to C as 1. Simple, like that. Okay? This is called adjacency matrix. But when you use this matrix with directed graph, you have to consider direction as well. Okay? Which is in contrast to the above. When your graph is undirected, with one edge, you need to set 2 ones. Okay? You have to set 2 ones, not 1 1. Like this. From A to B means you must have from B to A. From A to C, you must have from C to A. From A to D, you must have from D to A. That is undirected graph. But with directed graph like this, you have from B to A, not A to B. So you have B to A, not A to B. So A to B is 0. Is it clear? So that's how you can actually set the adjacency matrix. And the adjacency matrix can be extended to weighted graph. Whenever your graph is weighted, then instead of having 0 and 1, what you have is 0 and weight. Okay? Like this one. A to B is 1. A to B is 1. B to A is 1. A to C is 4. A, C is 4. Row C, column A is 4. Okay? Or A to D is 2. Then in your matrix, A, column D is 2. Row D, column A is 2. Okay? So that's mean in adjacency matrix, you can extend it from 0 and 1 to 0 and weight. Both in undirected or directed graph. Okay? As simple as that. Okay, and the problem of adjacency matrix is you need to create big metrics. Okay, big metrics according to the number of vertices. And this is one drawback, one problem. You can see that we have 100 vertices. Then you have to create 100 rows, 100 columns, just to represent 99 edges. To represent 99 edges, you need to create 100, which is 10,000. Okay? You need to create 10,000 elements in the array to store 99 values, 99 ones, which is not very good idea. It's very expensive. It's not cheap. So instead of create matrix, we might change it to limitless. So another scheme is called adjacency limitless. Is where we use an array with combination of limits. So basically, we have an array, one direction, one dimension array of vertices. Like in this one, we have 1, 2, 3, 4, 5, 6, 7. We have 7 vertices. We create an array of 7 elements. 7 elements. Each array, each element is represented with 1 limit. Basically, it's an array of limits, like this. Okay? We have an array, this is an array of 7 elements. Each cell store limits of destination. This means from A to 2, from 1 to 2, 1 to 4, 1 to 3. Okay? This from 2 to 4, from 2 to 5, from 3 to 6, from 4 to 6, 4 to 7, 4 to 3. Let's have a look at the picture. Let's have a look at 1. 1 to 2, 4, 3. 1 to 2, 1 to 4, 1 to 3. Okay? And if you look at 2, 2 to 4 and 5. 2 to 4 and 5. You can see that we only store out degree. Out degree. Okay? If you consider only out degree, then you have an array of out degree. Out degree of 2, we have 2 to 4 and to 5. Look at this note 7. 7 has 2 in degree, has 1 out degree. So 7 points to 6. So here 7 points to 6 point. Okay, so that's the graph that we have in adjacency limits like this. That's the limits created according to the out degree. So this is a limit of our algebras for each spanning each vertex. We can add weight on the limits as well. Okay, like this. B/1 mean the weight of A to B is 1. C/4 mean from A to C, weight is 4. D/2 mean from A to D, weight is 2. Okay, so that's how you can extend adjacency limits with weighted graph. Okay, so that's the basic of the representation of the graph. I would like to introduce data structure, visualization to you as well. Okay, and go to graph. If you go to graph, and we basically have no basic graph properties here. What we do is just click the first one, breadth search first. And then what you have is this. Okay, but what we are going to look at is, we can see that in this visualization, you can render different kind of graph. For example, directed or undirected graph. If you click on directed graph, a graph is random and is displayed undirectedly. Okay, you can choose small or large, with number of edges. For small, you have 8 vertices. For large, you have
18
vertices. Okay, and you have 3 different views. What you have seen now is called logical representation. Okay, so what I'll do is I'll change it to here, to small one, and what you can see, you can learn from this visualization is, we have adjacency matrix of this graph like this. Okay, the empty cell is 0. And you can look at its adjacency limits like this. That's the limits. Okay, and you can see that in this limits, the blue color is the note. The blue color is the note. And the black color is the weight. Okay? If I go to another graph like this, here we go. You can see that now the graph is weighted. When I click on the matrix, instead of having one, we have weights in the matrix. And in the limits, we have weights in the nodes as well. So node number and weight of the edge, that node. Okay? So that's all about metrics and limits representation for each graph. You can have a look at this example, okay, to see different kind of graph. Okay, so we have a 10 minutes break, and we will have one last topic to cover today, which is the algorithm that we are going to learn in this semester. Is breadth-first search, and another one is depth-first search. Okay, so breadth-first search and depth-first search, and you can actually run this algorithm here, undirected, small, here. Okay, and what you need to do is you have to start with one node. You have to type the name of the node. For example, 0 in this node, and click run, and it will show you how the algorithm works. Okay, so that's how algorithm works with this algorithm. Okay, you can actually play around with these two algorithms, breadth-first and depth-first, before we have a lecture in 10 minutes.
Josh. Oh, I see. Skills. Data structure. What's your GPA? What's your GPA? Hey, oh. What's your GPA? What's your GPA? Talas. Emphasize learning. Insert. Insert last. Next. Size last. Heap size. Last equal ทำไมต้อง this ถ้าไม่ใส่ this ถ้าไม่ใส่ this ตรงไหนปะ ยูจิมาอยากสอบ SSN อืมแต่เขาสอบดีleft right right rotation right ตัวเดียวเลยเฮ้ยตัวเดียวเลยฮีประจานฮีปีไฟอัพฮีปีไฟดาวปีไฟโอฮีไซส์โอ้ช่างมันสมองโอ้สนุกเกมสปีดมีคนเราเปิดหรือเปล่าเอาเก่า
มีใครขึ้นมายังไม่ได้เช็คชื่อได้ครับ
ได้ครับเก็บไปเลย
สริตาอยู่ลูกสริตาอัครนามชัชยาธนวดีธีรพัฒน์ธนศักดิ์ สิทธิ์ประปรัชอาทิพลศักดิโชตินักพีทัศน์พัชระฐานพัฒน์กระจ่างจันทร์ชะวินนะครับแล้วกลับมาดูกันที่ตัวนี้นะครับ basically we have two techniques two algorithms to cover today breakfast search and depth search by the name of breakfast search let's have a look and depth search. Let's have a look at how it's defined. A breadth-first search algorithm, starting from a vertex 0, then you have to visit all vertices around vertex 0, from left to right, according to adjacency limits. Okay? Which means if I go to this limit here, if I start from 0, I must go to 1 followed by 4 first. Okay? If I use the starting point at 1, I must go to 0, followed by 5, followed by 6 in this sequence from left to right. However, if I use metrics, we will also follow from left to right according to the status 1. From 0, we'll go to 1, then go to 4 later. Okay? Or if I start from node 1, the first one to visit is node 0, followed by node 5, followed by node 6 in this order from left to right. Is that clear? Okay? According to what adjacency limits or metrics. Okay? So basically in metrics we start with we put in the order from left column to right column. In the link list, just follow the list of the link list. Okay, the order of the link list, and that's it. Okay? And that's the breadth-first search. Okay? So basically, what we're going to do is we are going to start from one node only, and we are to visit all the nodes around it. Okay, let's say every node which has an edge connected to this node must be visited first. Afterwards, we will put every node around the starting point in a queue. Okay, and that queue will be used for the repeated loops like this. Okay, so I just go back here once again, and what I would like everyone to look is look at this matrix, this limit first. You can see on the left hand side here, you have Q. Okay, so what I'll do is I will slow down, starting from vertex 0, Okay, and I run BFS. You can see that at vertex 0, we have the first node to visit is 1. Okay, and the first node 0 is actually in the queue already. This is the queue. Okay, and then when we know that from 0 to 1, we are going to put 1 into this queue. 0, 1 in the queue. Okay? And then put 4 in the queue. Can you see that now we have 0, 1, 4 in the queue from the linkers. Okay, from the linkers, 0 is starting point, 1 and 4 is 2 visited node. After you put the last node in the queue, what you need to do next is delete the front of the queue. Delete the front of the queue. DQ. So when I click next, 0 is gone. 0 is gone. We have 1 and 4. Okay? And then at the front of the queue, we have the new fronts. New front is 1. So the whole process is repeated. At 1, you have 0, 5, 6. Let's have a look. Once again. At this link is 1. Link is 1. We have node 0, node 5, and node 6. So basically we are going to put 3 nodes in the queue. Okay? Put 0, 5, 6 in the queue. However, we have to make sure that every node can only be put in the queue or in queue when it has never been visited before. Okay? And here you can see that node 0 was visited already because it's the first node. Basically it means it has been in the queue and the queue already. Okay? So 0 will not be added twice. No. Every node can be added to the queue once and only. Here, 0 will be skipped. And the next one is 5, which is never been in the queue. 5 has never been in the queue before, so we have 5 in the queue. 6 never been in the queue, in queue. So now you can see that your queue has 1, 0, 4, 5, 6, and that finish the link list 1. Okay? When link list 1 finish, when you finish the link list, DQ. So now you are going to remove 1 out of the queue. That's it. Okay? So once again, what do we do? Take the front of the queue and explore the link list of that node. Okay? Put everything in the queue if that node never been in the queue before. Okay? Never been visited, never been in the queue before. So put it in the queue. After you finish, remove the front of the queue. That's okay, that's the end of one loop. Then go back again. The front of the queue, 4. Okay? And we have a link list of 2 nodes, 0 and 6. Check 0. 0 has been in the queue before? Yes, skip. 6 in the queue before, yes, skip. And the end of the queue, DQ. Okay, the end of linked list, sorry, the end of linked list, DQ. That's it. Is it clear? Is it clear? Okay. Now we have 5 at the beginning of the queue. Go to linked list 5. And linked list 5 we have 1 and 3. 1 and 3. So we starting 1 has been in the queue before, skip. 3 never been in the queue. 3 never been in the queue. How do we know? You can see that we have this flag for each node, true or false state. Visited, false means never been visited. It's very true, which means it has been visited already. Okay? So we have this special array set up as a flag of each node has been visited, yes or no. 3 added to the queue, and that's it. Again, now the front of the queue is 6. Then go to 6, we have 1, 4, 2. 1, 2, 4. Is that clear? Everyone, I will change this representation from linked list to matrix. Matrix. It's actually the same thing. Okay? So instead of traverse along linked list, we just search for 1. And we can see that in matrix, in linked list. In linked list, at linked list 6, we have 1, 2, 4. 1, 2, 4. Please have a look. We're going to change it to matrix. 1, 2, 4. Same thing. Okay? So what we do again, we are going to explore 1, 2, 4. Check if 1 has been visited. It's true. So skip. Next, 2. Has it been visited?
Nope.
So put 2 into the queue.
Sure.
Okay? That's it. If it's false, never been visited, put it in the queue. And update it to true. Visited status to true. Now, next is this 1, which is column 4, vertex 4. Okay? Again, 4 is true, which means has been visited. Skipped. Let's skip. Again, you have done with this row. No more ones. No more ones. So, finish. What do we need to do? DQ. 6 is deleted from the front of the queue. 3 is the new front. And again, the whole process is repeated. Is it clear? That's how we use this queue to implement breadth-first search. Is that clear? Is that okay? Okay. Now, with this representation, you can change between linked list or matrix. Okay, to explain how this algorithm has been implemented and how it works. And you can see that we have spatial array here. Visitors. We need it. Okay? We need something. We need a spatial data structure to help us identify or to keep track of the status of visitors for each node. And that's it. Okay. what I'll do is I will go to the next algorithm, depth first search. This one is a traversal in graph as well, but it's implemented differently on different concepts. Just have a look. Okay, in depth first search, we basically doing something like when you have a tree, sorry, not tree, a node, starting from that node, instead of explore every node around it. No, we don't do that. On the other hand, we select one node to explore. From node A, if we have 3 nodes around A, select one of it. As soon as B, then from B, we will extend to the next node next to B. Okay? And you should remember, we have some other nodes around A. Let's say we'll come back later. We come back later. Okay? So this is one example of depth first search. Let me introduce a very basic one. Let's have a look at this node 6. Everyone, look at my graph. We have a node 6 connected to 3 other nodes. Okay? 6 connected to 4, 6 connected to 1, to 5. So we have 3 choices. Okay? What if I start with 6? 6. Okay? And I will run the FX.
Oh my god.
Start with 6. With 6, we have 3 choices to go. Okay, if you look at this linked list, 6, we have 1, 4, 5 nodes to go. We have 3 nodes to go. We start with the first one first. Start with the first one, 1. And what do? We start with 1. Please have a look here. When we go to node 1, okay, we are not going to finish 4 and 5. We leave it. Okay? So we jump to linked list 1 immediately. That's how we do. Okay? 6 to 1. In the previous one, we have to finish 4 and 5. The first one. But this depth first search, no. At 1, we not followed by 4 and 5. We skip to linked list 1. At 1, then we go to 1. Immediately. Okay? And at linked list 1, you have 3. What else? Go to 3. When you have 3 here, go to this linked list 3. And you go to 1. Okay? However, we have one basic similar rule. That is, you will go to this linked list whenever that node has never been visited. Okay? So you still have this visited status. Okay? So if I skip back, starting from the first step, okay? From 6 to 1. 1 never been visited, we can go to 1. So if 1 has never been visited, go to 1. Now we have 3. Check the visited 3. 3 has never been visited. Never been visited. Go to 3. Go to 3. And then we have 1. 1 has been visited. 1 has been visited. So don't go to 1. Don't go to 1. Skip. But we don't have the next note in the lingless. Okay? When we have no other notes in the lingless, we have to go back. We have to go back. And when we go back, we call it backtrack. Backtrack. Because we come to 3 from this lingless. Remember? I just skip, step back. We come to 3. We come to 3 from 1. And then at 3, we have no way further. Okay? So we go back from 3 back to 1. And we have the next note. You can see now at lingless 1, we go to note 6 because we finished note 3 already. Okay? So we go to note 6 and then 6 has never been visited, then go to 6. Yes or no? No. See, 6 has been visited already. So we don't need to go to 6. And lingless 1 is finished. Lingless 1 is finished. So now you finish lingless 1, lingless 3. Finished already. Go back again. Lingless 1. How did we get to lingless 1? We come from 6. Remember? We come from 6. You can see that. In this algorithm, we need to remember. We need to remember which node has been coming from. Okay? We have to remember the node which we coming from. Node 1, lingless 1 has which node come from, sorry, which node goes to 1? 6. 6. Okay? We come from 6 to 1. So that means we have to go back to 6. And you can see that everything that I have explained about memory, we have to remember which node we coming from is actually written on the left-hand side. We have this. Written. From 6, we go to 1. From 1, we go to 3. Okay? Step by step. And from 3, go back to 1. From 1, back to 6. Okay? We only go back or backtrack. Remember this keyword. Go back is called backtrack. When that lingless is finished. We finish the whole lingless. Okay? And again, now we add lingless 6. Node 1 has been done. We are going to move to the next node 4. And 4 has never been visited, so we go to lingless 4. Again, you can see that now. Here, we are going to visit lingless 4. 4 is listed here. Okay? 4 coming from 6. 4 coming from 6. The indents can give you this, the 6 to 1, 1 to 3, 6 to 4. Okay, because it's indented. Again, 4, we have one note, 6. And 6 has been visited, so skip to next note. And we don't have the next note, which means finish. Then backtrack. Whenever to the end of Linus, backtrack. And backtrack means from 4 back to its parent 6 again. So now we are going back to 6. And 6 we are going to go to 5. And 5 has the big visited, so go to 6. Go to 5. And 5 we have 6. 6 has been visited? Yes, skip. Next, 7. 7 has never been visited. Go to 7. That's it. Okay? What you need to check if this visited. If it has never been visited, go to that limits. And starting to follow each note one by one. 5 has been visited, skip the end, go back to 5. So 5 has been visited, go to 5 and finish. And that's it. Whenever every note has been visited, I mean all notes are visited, then the algorithm finish. Okay? This data structure, Linus can be easily viewed, but if you have metrics, what you need to do is you need to process every columns which has 1. That is the next node to be visited. Okay? So I believe this algorithm is a little bit more complex than the first one. Okay? So that first search will be shown again. I'll show you once again with a little bit more large graph. Now the graph is large. And you look at the representative is here. Okay? So what I've heard, I will let you look at the logical view of this algorithm. And when you look at this logical view, you can see that it's actually when you have a machine from starting point and you drill a machine from the surface of the soil, and dig down until you can go further, then go back and find another to go deeper. So let's have a look.
2, 4.
Okay, starting from this graph, I was starting from
Check
one
7.
here.
7's
One
already
here.
gone. So
Okay, let's say 0 here. 0 is 0 is here, starting from this node. Run from 0, okay, go to 1, and from 1, go deeper
Oh, fuck.
to 4, and from 4, think further to 5. See, we try to go further from the starting point, from 0 to 1, to 4 to 5, and from 5 to 6, 6 to 2, and then from 2 we can go to 8 and go back to 6, to 3, and to 3 we go further to 10, and from 10, can we go further? Yes, we go to 9. From 9, can we go further? Yes, we go to unvisited node 8. From 8, we can go to 7. From 7, we can go to 11. You can see that every time that we consider a node next to the note, we must go to unvisited note. Okay? We have to choose the unvisited note to go to next. And if you look at this blue arrow, you can see that the next step that we choose is always away, one step further from the starting point. Okay? It's always go further, deeper. That's its goal. That is why we call deep depth research, deeper. Okay? And that is how you can see depth research works. Okay? Once again, if I slow it down. At 11, you have 12, and at 12, you have, let's have a look. At 12, you have 1, 2, 3, 4, 5. Okay? Once again, we start according to the sequence. 8 first. 8 has been visited? Yes. Don't go. 9 has been visited? Yes. Don't go. 13 has been visited? No. Go. Okay, that's it. Yeah, visited, don't go. 9, visited, don't go. 13, visited, no. It's free, it's available, so go to 13. That's it. Always go to unvisited node. Then from 13, do we go? 10? No. 12? No. 16? Yes. Unvisited. And from 16 to where do we go? Everyone, please have a look. At 16, we have one way back to 12. 12 has been visited. Don't go. 13 has been visited. Don't go. And we can see that we have no other ways. We have no other ways because 16 has only 2 ways. And both 2 ways lead to visited node. It means we finish. We finish at 16. Backtrack. Okay? When that node is finished, please have a look at which node leads to 16. And the node where 16 coming from is 13. So we go back to 13. Backtrack. We backtrack. Let's backtrack to 13. And then next, go to 17. 17. Can go to 3? No. You see that? 10? No. You see that? 13? No. 15? Yes. Never been visited. And from 16, can we go to 11? No. 12? No. They are visitors. Finish, backtrack. Where does 15 coming from? Where is it coming from? Is it coming from 17? Go back to 17. And 17, finish, go back to 13. Whenever it's finished, go back. Go back to its previous. Okay? And 13 back to 12, 12 back to 11, and 11 goes to 14. 14 has no way out, so go back to 11. 11 go back to 7, 7 go back to 8, 8 go back to 9, 9 go back to 10, and 10 go back to 33, 3 back to 6, 6 back to 5, 5 back to 4, and back to 1, and back to 0. Whenever you go back to the first note, that means the algorithm finished successfully. Okay? The algorithm to its starting point, the first note. And there you have this finish. Okay, so everyone, I would like to show you once again a comparison breakfast search. Now I would like to show you with this, sorry, skip back. Last graph. New graph. Okay, let's have a look. This graph is a little bit bigger and it's shown in logical view. With this one, you can see that the difference between breadth-first search and depth-first search. I'll start with this note 0. Okay? Again, in depth-first search. Starting from 0, we start to go deeper away from 0. You can see that. But here, in breadth-first search, what we do is, we are going to, the concept is we are going to explore every note around 0 first. Every note around 0 first. Breadth means wide. Okay? Explore from 0. Let me create a new one. Okay, this one, starting from 0 and run BFX. 1, see, and not from 1 back to every note around 0. You can see that we have 4 notes around 0. These 4 notes must be visited first. You can see the difference between depth-first and breadth-first search. That's the main difference. Okay? Explore the nearest first. Okay? Explore the nearest. If you look at these algorithms, many people have it as a metaphor of when you drop a small pebble in the water. And you see, right? Starting from innermost, further, and the way starting bigger and bigger. And that's the concept of dropping a stone in water. Breakfast search. Next, it will extend from one edge away from 0. Now we're going to extend to 2 edges away. 2 edges away. 2 edges away from 0. See, you have 5. And 2 edges away from 2. Okay? So you can actually go and explore these 2 algorithms once again. Okay? These 2 basic algorithms is used many times. And again, the 2 algorithms are used like in tree. It's systematic. Okay? The reason that we have back in the tree, we have in order, we have pre-order and post-order. Just because they are the systematic technique, the system to explore everything without redundancy. Okay? The concept of traversal is you must be able to explore everything. Don't leave a note. But do not visit one note twice. One note once visit. Okay? For each note you have to visit once. And these 2 techniques is proved to be successful for those 2 questions. Don't leave any note behind. And one note, one visit. Okay? That's how you actually explore the graph. The last topic for today is the different. difference between two. Okay? You can see that. First of all, this table is the whole picture. Okay? DFS stands for breakfast search. DFS stands for breakfast, obviously. Yeah? Basic structure. Remember this. In breakfast search, we need queue, but in depth search, we need stack. Queue and stack. Okay? Because here we need to remember in sequence. Here we need to remember what we did before. Okay? So we need queue for breakfast search, stack for depth search. And
Oh.
the conceptual difference is very important. VFX build the tree level by level. Okay? Basically, we are going to explore level by level, which means from starting point, explore 1 edge away first. Then explore 2 edge away, 3 edge away. Okay? So that's called level by level. But here, depth search, build tree, subtree by subtree. So we are going to create from 1 edge downwards, okay? And we come back to the original root when this subtree has been explored successfully, finished, okay? And yeah, the approach, because it's queue, it's cipher. And therefore such, it's static cipher. What are they suitable for? Whenever you are using breakfast search, it's more suitable for searching closer, the vertices closer to given source. Basically, whenever you want to explore whatever near to the source, using breakfast search. Okay? And whenever you are thinking the solution is away from the source, it's better, use breakfast search, depth search. And here are the applications you need to read it, okay? Breakfast search is used in find the type graph, shortest path, that's one thing. And in depth search, we use it to identify acyclic graphs, okay? This is very interesting because in depth search, everyone, we are going to finish just in a second. When we use depth search, to explore graph, there are some link, some edge. Let's have a look at it here. Okay? You can see that this depth search algorithm finished already. It's finished. Okay? But we use only some edges painted in blue. Okay? Blue means use in proposal. Okay? And this one is not used. This one is not used. This one is not used. Not used. Okay? Now, we have 3 types of not used edge. Okay? For every edge used in the algorithm, blue is called 3 edge. You have to know 4 types of edges.
Oh.
Okay? 4 types straight edge, back edge, cross edge, and forward edge. Okay, let's have a look at this one. For example, if you have an edge used in depth first search, it is called tree edge. That's the easiest one. Okay? For those edges which are not used, those edges which are not used, you have to differentiate between three types. Forward, back, or cross. Forward, back, or cross. How do we know which edge, which unused edge is forward, back, or cross? You have to draw. You have to draw tree of depth first search traversal, which means let me show you the picture. It is easier to look at. Okay. Okay. This is example of the tree. Okay. Assume that you have a graph, and then you use depth first search, starting from node 1. And from node 1, you go to node 2, go to node 4, go to node 6. And then you backtrack to 4, backtrack to 2, backtrack to 1, then from 1 go to 3, go to 5, go 5 to 7, backtrack to 8. Okay? You can see that whenever you visit a new node, draw it in the next level. Okay, so basically from the algorithm like this, depth first search, starting from 0 to 1, 4, 5. So basically you have 0, down to 1, down to 4, down to 5. Okay? For each visit, go down, down, deeper. Okay? One level below its parent. One level below its parent. And after you finish drawing this graph or this tree, whenever you finish drawing this tree, what you need to do is all unused edges, you have to draw it as well. Okay? Draw unused edges and look at the direction. If the direction is from a node back to another node in the same path, it's called backwards. Back, same path, back. Okay? Or this one, it's from top to bottom. Top to bottom is called forward. Okay? From bottom back to top, back. From top to bottom, forward. Okay? And if you have a special edge from one path to another path, you can see that it's from another path. This one, 5, is from this path. 4 is from this path, on different path. When they are on different path, we call cross edge. Okay? So basically you have to draw the tree and look at the path. If there is an edge in same path, look at the direction. From top to bottom, forward. From bottom to top, back. From different path, cross. That's it. Okay? And we need to identify 1, 2, 3 types of the edges. Everyone, take a note. If you have the original graph, undirected graph. Okay? Undirected graph. Like this. 4 types of edges. 4 directed graph only. Okay? But if you have undirected graph, you will have only two types of edges for undirected graph, which is straight edge and back edge. Let me put some pink and blue. Okay? If you have directed graph, you can see 4 types of edges. But if you have original graph is undirected, you will have forward and cross. You won't have forward and cross because you don't have direction. Okay? All you have is 3, the edge in a rhythm, and the unused is baggage only. That's all about the edges, different classification with the depth search algorithm on graph. Okay, that's it. Okay, so this is all the thing that we use for our final exam. Okay, and next week, I plan to have your test today. จริงๆวันนี้ตั้งใจว่าจะเก็บคะแนนอะไรนะครับ AVL แล้วก็ HEAT บางมื้อมีประชุม 11 โมงพอดีเลยนะครับก็เลยจะขออนุญาตเลื่อนไปเป็นสัปดาห์หน้าเฉพาะเก็บคะแนนนี้นะครับทุกคนคราวหน้าเราจะมีเก็บคะแนน2 เรื่องด้วยกันเนาะคือ AVL 5 คะแนนแล้วก็ HEAT อีก 5 คะแนนจากโค้ดที่ให้ไปอ่านจะได้ไหมครับนะคราวนี้เนื่องจากว่าเป็นสัปดาห์สุดท้ายผมจะไม่เรียกทีละคนละผมจะให้ทุกคนนั่งประจำที่โอเคไหมครับนะเพราะฉะนั้นสัปดาห์หน้าให้มองว่าเป็นควิสย่อยของแลบแล้วกันนะครับจะห้ามขาดนะสัปดาห์หน้า2 ควิสเลยนะ AVL กับอะไรครับ HEAT 2 เรื่องโอเคไหมครับเรื่องกราฟ
ไม่อยากออก
ก็ไม่ทัน
อย่าออกเลย
โอเคนะครับมี 2 เรื่องเนาะการเรื่องกราฟที่ใช้ในการสอบไฟนอลไหมใช้โอเคไหมครับเนาะวันนี้อาจารย์ต้องขอเริ่มเร็วนิดนึงก่อนจะมีประชุมตอน11 โมงนะครับเพราะฉะนั้นสัปดาห์หน้าคือสัปดาห์สุดท้ายให้คนเตรียมตัวให้ดีเนาะอยากให้ทุกคนได้เต็มทุกคนนะครับสัปดาห์หน้าให้เอากระดาษมาด้วยให้กระดาษอาจารย์ให้เอาดินสอปากกามาด้วยนะครับเดี๋ยวอาจารย์มีกระดาษให้เอาดินสอปากกามาจะได้มาเขียนต่อในห้องได้นะครับมีใครมีคำถามอะไรไหมครับเหมือนเดิมครับกระดาษ A4 1 แผ่นจดได้15 บาทแล้วก็บ่ายวันนี้เราจะมีผู้เชี่ยวชาญนะครับทางด้าน Data Science ทางด้าน Data Analytics มาจัดบรรยายพิเศษที่ชั้น 10 ห้อง 1006 นะครับถ้าใครสนใจเข้าไปฝากหรือจะฝากเนื้อฝากตัวกับพี่ใหญ่เพื่อจะเข้าไปฝึกงานกับบริษัทใหญ่ๆระดับโลกเข้ามาจากบริษัท SAS SAS นะครับเป็นบริษัทซอฟต์แวร์ใหญ่ระดับโลกเหมือนกันนะครับอยากจะเข้าไปฝึกงานอยากจะเข้าไปมีโอกาสรู้จักกันก็ไปให้เขาได้เห็นหน้าเห็นตาเรานะครับ 6นะครับอันนี้ก็เชิญไปได้เลยนะครับสำหรับวันนี้เชิญเข้ามาเป็นพิเศษโอเควันนี้ก็ขอตัวเท่านี้นะครับทุกคนนะครับไม่มีใครตามตัวเลย
ส่วนมากเป็นไรเดอร์นะไม่ได้เกิน5 คนหรอก